Alright guys, welcome back. We're going to do another tutorial today, and this one's the water, an essential for life. Now again, we're back into the science thing, and we're really into the actual details right now. So water is actually a really important molecule for all of life, and it's for a couple of reasons. I'm going to start you guys off by having you go to page 5, and it's going to introduce your um, your main properties of water that we're going to look at here with Plato. Granted, there are some other properties of water that are pretty useful outside of these ones listed, but these are the ones we're going to focus on in Plato. All right, and you'll notice that they have a list down there in the second half of your page. It's polarity, cohesion, adhesion, density of ice, high heat capacity, and high heat of vaporization. All of these are important, and we're going to talk about these, but I have a feeling that they're going to describe them page by page after this, so I'm not going to describe them all right now. You're welcome to look over it. So I'm going to move on to page 6. All right, it's just talking about the chemical structure of water. First off, water, as you guys already know, is shaped like this. So you have an O, and then you have two H's attached to it. One thing I want you to notice is that you always see it in this weird little triangular form, right? So you got like that up, down, over kind of thing. And the reason it's always drawn in this triangular form is because this is technically wrong. Like that. Can't do it. And this is technically wrong. And here's the reason why. So this oxygen is very electronegative. You can think of it as just like bigger and stronger than the H's. So what happens is that in this covalent bonding, there's not an equal sharing of the electrons. So normally an electron would be like right, I don't have a pencil, right here in the middle of your O's and H's, right? It'd be directly in the middle. But because O is more electronegative, what happens is that you actually end up with a situation where your H's are pulled really, really close to your O. Alright? As opposed to being halfway like this, now they're like right there, right up next to your O. And because of that, your O, your oxygen, has a slightly more negative charge than your H's. That means your H's become slightly positive. This is called polarity. Okay? So polarity is where you have different charges at different points of your molecule. Normally, molecules are just either overall negative, overall positive, or overall neutral. In some cases, you have polar molecules like water or salt and these kinds of things where you actually have an uneven distribution of those charges. All right, so you have a slightly negative oxygen, slightly positive hydrogens, and because of this feature, it causes this triangle shape. These H's start to bend away from each other. Like technically, your O's would look something more like this. But because these are both positives, you guys know that if you put like two sides of the magnet that are the same together, they bounce away from each other. So it causes this slight bending feature to where the H's are out. Okay? So that is why water is polar. That is what the definition of polar. Now, how that is relevant to life and to you guys, polar things dissolve other polar molecules. So like breaks down like is something that you're going to hear if you ever get to college chemistry. It's just like dissolves like. So polar things dissolve polar things, non-polar things dissolve non-polar things. So that's why when you put like water and oil together into a cup, you just kind of like spread them around, and then you stir it up. Yeah, you can get them mixed. You'll see little like globs and whatnot, but you can like mix it all up. But if you let it sit there, it'll separate out again to where half of it is going to be water, half of it's going to be fat or oil or whatever it is. So one thing about this polarity is that the reason your body doesn't break down fat so easily and why your body uses fat is because fat can't be dissolved so simply by water because it is nonpolar. And this is one of the reasons why fat's so hard to break down. But early in life, where nutrients weren't as readily available, so you had to go hunting, you had to go kill a gazelle or whatever the heck it is with a spear, and then you eat your gazelle. You worked out a lot back then, and you never knew when food was coming, so your body uses fat to store your energy. Okay, so way back when it was super useful. Now it just kind of kills us because you want some food, you just go over to McDonald's at 3:30 in the morning and order yourself like a heart attack burger, and you get fat, right? So it's a lot harder to burn off fat now because A, we're not chasing around wild animals, but B, because food is so readily available. All right, and that is one thing about the polarity of water. Whether or not this is a benefit or not is kind of up to you. It was, This was a good thing way back when. It's less good now. Really, we should all just be dying. Anyway, that's like a whole other issue. So that is the polarity of water. We're going to go ahead and move on to page 7. They're just talking about polarity again. They tell you the exact degrees. So like I drew mine a little differently, but if you look at the one that they described in their water molecule, it's 104.5 degrees. So they've calculated all that out. I don't really know how relevant that is. You don't need to memorize this. We're going to move on to page 8. Cohesion and adhesion. Okay, so we've talked about polarity. That's great. So we're going to move on to cohesion and adhesion. I'm also running out of paper, so if you guys see like me write on the back of something, it's just because I don't want to go over to the other portal and get paper. So, adhesion, cohesion. It's a pretty simple distinction, kind of. Here's adhesion, cohesion. Alright, the simplest way that I've defined the difference between cohesion and adhesion is cohesion is sticking of two of the same thing, or of groups of the same stuff. So this is kind of like water sticks to water. I don't know, what are some other examples? You know, skin cells stick to each other. Wow, that was a really weird kind of example, but it's true. So they stick to each other. Anything that sticks to itself, essentially, so water to water, skin to skin, that is cohesion, as in they go together, they are cooperative. We've seen this co-word before, okay? So cohesion means they're the same thing sticking together. Adhesion, ad is from the Latin ad, which just means to or towards. So this is sticking towards something else. So this would be like, I don't know, water. Oh, sticking to paper. There you go. Sticking to paper. Or sticking to salt. You know, whenever you have salt and you get a little watery, you get clumps, right? I keep banging on this table. I'm sorry. I'm going to stop doing that now. But every time you get salt and you water it down, it kind of sticks together. If you add just a tiny bit of water, you get weird little clumps of salt, right? So this is an example of adhesion. Adhesion really literally is just the sticking of one thing to another thing. So cohesion is actually a type of adhesion. It's the sticking of the same things together. So water to water. Okay. So adhesion, different things. Cohesion, same things. All right. And that's really all you guys need to know about adhesion and cohesion. As long as you can tell them apart, you're all good. They'll probably talk about it more, to be honest with you, in your tutorial. I'm not really sure how important it is for you to know these kinds of things, but cohesion, like that water to water sticking, that's why when you fill up a water cup, you can see it rise over the edge just a tiny, tiny bit, like over the top of the water before falling out, right? And that's because of something called surface tension. So it really just says water sticks to each other. So even if you put them over where they're supposed to be, they'll hold each other in the cup. All right, that is called cohesion. Adhesion is kind of like how adhesive bandages work. So, you know, you get a cut on your finger or whatever, your hand, and you put a band-aid on it and it just kind of sticks to your hand. That's called adhesion. So that obviously band-aids are not made out of skin. So it's not skin to skin sticking. It's band-aid sticking. Whatever. So adhesion, different things. Cohesion, same thing. Okay? So page 9, they're going over the properties of water and capillary action. So that's a good example of adhesion, actually. So we just talked about adhesion. Capillary action is the adhesion of water molecules to other substances. I just told you this earlier. So I guess if on the mastery test you hear capillary action, that is the process of adhesion. All right? It's just water sticking to stuff. And capillary action is specifically blood and your, skin, but whatever. Page 10, they're going to give you a little experiment. That's weird. Okay, so let's be honest. These experiments, they're kind of... I would love for you guys to do experiments. I don't mind if you try this, but really, if you take an empty cup and you put a cup of water and you stick water in the one with water and one in the one without, clearly water will run up and soak into your paper towel in the wet one. Right? things get wet. So don't do the dumb experiments, but if they make sense and you're curious to try them out, absolutely give it a chance. All right, so they go over surface tension on page 11. I told you that surface tension is over here in cohesion, so we talked about that just a second ago. My bad, I guess I was jumping the gun a bit. No worries. So we're going to go ahead and move on to page 12. Just kidding. 13. Okay, cool. So 13. Water is generally a solvent, so it generally dissolves other things. There's just more of it than other things. So it dissolves a lot of stuff. And remember I talked about polarity earlier, so it mostly dissolves polar stuff. Oh my gosh, another activity. So I'm going to move on to page 15. Was that it? Really? They just talked about it dissolving? Okay, so they kind of skipped it. They gave you this gigantic page of solvent behavior. I already told you, solvent behavior. Solvents dissolve things. So water dissolves salt, dissolves sugar, dissolves, I don't know, God knows what else. It dissolves other water, like ice, you know. So it dissolves plenty of stuff because it is polar. So we're going to go ahead and move on. Density. Okay, so water's density is fluid. So here is, oh, this is going to be bad. Is an ice cube. Okay. This is a water puddle. Okay. Puddle. And this is it's a pot with a handle on it. And here's steam. Okay. So steam, boiling water, that is steam. All right. You have 3 states of water. You've seen all of these things, but the thing is that their densities change depending on which form it is. So water has a fluid density, as in it changes a lot. An ice cube has a high density, because then the water molecules are packed real closely together. They can't move because they're way, way too close. It's kind of like when you stick a bunch of people in the portable over there, or if you were to stick a bunch of people in like a subway train, or I don't know, think of a place where you've been really crowded. It's really hard to move. That is what an ice cube is. All right. A puddle, on the other hand, is more like, so I'm going to call this moderate density or like medium density. I'm going to use the word moderate because I like that one more. So you have a moderate density over here in liquids. So liquids have just kind of, people are still moving around. It's fluid. They're moving in and out of the room. So your party's not completely packed. Maybe you've got like, I don't know, 10 people in the portable, as opposed to over here with the ice cube where you've got like 60 people in the portable. All right. And then steam is where it has like low density. It has virtually no density. Like everything is so far apart. This is kind of like if we were in the portable and there are 3 of you guys and there's just me. That's 4 of us. We could sit in 4 different corners of the room and just chill and be nowhere near each other. All right. So if you want to think of it that way, an ice cube is like a really packed room. A puddle is like just a comfortable room, and steam is like an empty room. You have virtually nobody there. So there's a lot of space. All right. So density is literally how close things are together in a larger object. All right. So that's all density is. And water just happens to have several forms. Pretty much everything has these several forms. You'll find that there are certain things that you cannot turn into liquids and solids and gases and whatnot, at least not naturally in nature. Like gold, you'll generally find it in solid form, but you could absolutely turn gold into a liquid. And technically, if you were to heat gold enough, you could turn it into a gas. Technically, like I said, technically you can turn anything eventually into a gas, but that's really weird. So, we generally don't do that with metals. All right, I've moved on to page 17 now, heating and evaporating. I just told you this. Just keep in mind, when we're here, it's high density, so everyone's packed together, right? Like packed tight. What's going to happen is that there is virtually no movement. All right, there's very little movement in this situation. In this puddle, however, we're just kind of packed okay, and there's a little movement. It's fluid movement. So it's not fast, it's not slow, it's comfortable movement, right? Everybody's just moving in and out. And over here in this one, if you had like a bunch of really hyper kids and whatnot, this steam situation would be an empty room filled with like 4 little kids. They're just running everywhere. So running everywhere, just like all over the place. Okay, so Oh gosh, I keep writing on this table. Sorry, Ms. Lundy. Anyway, so you've got ice cubes, puddles, and steam, and they're just different all across. So that's all this heating and evaporating thing really says. It's that in this empty room, you can run around as fast as you want. In the liquid room, you can't run around as fast because you're going to keep bumping into people. In this room, you're literally standing right next to everybody else, so you cannot run around. Like, you can barely move your legs. Okay? So that is how heating works. Let's see if there's any others that you need to go over. Let's take a look at slide 18 or 19, sorry. Yep, so 18 is an exercise. 19, it looks like they've given you links to go elsewhere. Huh. That's weird. So if you look on your page in Plato, it'll give you a bunch of links to talk about heat capacity and what was heat capacity and heat of vaporization, etc., etc. Let's talk about those a little bit more specifically and a little bit more about how you'll see them. So heat of vaporization. So vaporization. To vaporize, you guys actually know what vaporization is. Vapor is like a gas, so vaporization is when you steam stuff. So like when you boil water and it becomes steam, that is called vaporization. It has a really high heat, as in it's hard to boil water. Now you might not think that because you boil water all the time to do things, but boiling water takes a lot of time. Like if you do it over the stovetop, you can plug your thing up to high. It still takes you like 10-15 minutes, right? There are so many things in the world that are so much easier to boil. The reason that it's harder to boil water than it is to boil other things is because if it wasn't, our bodies would overheat. Like we'd literally explode from all the steam inside us and we wouldn't be able to live. In the same token, this is actually directly related to heat capacity. Water also has a very high heat capacity. Now, the difference between heat of vaporization and heat capacity is heat of vaporization is how hard it is to boil the water. Heat capacity really just says how hard is it to heat the water, even a little bit, heat the water at all. So like 1 degree. Okay, so it's actually really hard to heat this, just like it is with vaporization. These are entirely related. If you have to pick between the two, this one says how hard it is to boil. This one says how hard is it to heat up, just at all. Like just make it a little warmer, move it up from 70 degrees to 72 degrees, right? So that is heat capacity. It's just how much energy it takes to heat up a little tiny bit. All right, so they are one and the same essentially, and they're both reasons why our bodies are made up of largely water. We're somewhere around 70% water, and if we were, some other substance like alcohol burns really, really easily. It doesn't ever freeze, but it burns super easily. You can flame off alcohol with no problem whatsoever. So if our bodies were made of alcohol or something like that, every time we stepped in the sun, we'd overheat and we'd have strokes and we'd probably die. All right, but water has a good tendency to resist heating and cooling, so it also means that we don't freeze as fast. Okay? Any questions about this, feel free to send them to me in email or messages. I know we went through that kind of weirdly. Water is kind of a basic topic. You guys already know most of it, so you just have to get used to it, hearing all these terms. You guys have already seen all these things in action, so just try and memorize the terms, and you should be great on your master test. All right. Any questions, just let me know, and thanks so much for watching. I'll see you guys next time.